Does the reality we see fit predictions of a reality generated by the infinite computations inherent to causeless arithmetical truth? For that matter, what are the predictions? At first blush, it seems impossible to get any useful predictions from a theory that includes all computations and all observations. For if they all exist, any observation is compatible with the theory. As Victor Stenger noted, theories that explain everything explain nothing. Fortunately, there is a catch: not all observations are equally likely. If our conscious states result from the existence of all computations, then they are subject to the rules of algorithmic information theory. This enables us to make testable predictions, and thereby tie it back to hard science, observation, and measurement. Some of the predictions of this theory provide clues to otherwise unsolvable questions in physics and cosmogony. These predictions offer answers to such fundamental mysteries as: why the universe obeys simple, mathematical, life-friendly laws. Why empiricism, i.e. experimental reproducibility, works. Why Occam's razor works. Why the laws appear fine-tuned for life. Why the laws are quantum mechanical. Why uncertainty and randomness exist in physics. Why infinite descriptions are needed to explain any occurrence. Why observation and information are fundamental in physics. And why the universe has time and a beginning, for example, the Big Bang. These results are the work of pioneers in the theory, who include Bruno Marchal, Max Tegmark, Russell Standish, and Marcus Muller. Using the tools of computer science, math, information theory, and algorithmic information theory, they revealed how these traits of the universe result from our mind states being computationally generated. Quote: the appearance of a universe, or even universes, must be explained by the geometry of possible computations. Bruno Marchal in The Amoeba's Secret, 2014. Let's review the evidence for this most speculative of theories, which is presently at the forefront of mathematics and physics. Why laws? We take for granted that our universe obeys laws. But why should it? What's the source of these laws? Why are they so simple? Why aren't they ever violated? Why these laws and not others? All these questions are mysteries left unaddressed by science. Quote: in the orthodox view, the laws of physics are floating in an explanatory void. Ironically, the essence of the scientific method is rationality and logic. We suppose that things are the way they are for a reason. Yet when it comes to the laws of physics themselves, well, we are asked to accept that they exist reasonlessly. End quote. Paul Davies in the Flexi-Laws of Physics, 2007. Quote: with the equations, when they are not too complicated, we can predict phenomena. But in truth, the equation doesn't explain anything. It compresses, certainly, in a very ingenious way, the description of the physical world. But it does not explain the nature of bodies, nor why these bodies obey laws, nor from where these laws come. End quote. Bruno Marchal in The Amoeba's Secret, 2014. That laws are never violated, on its face, seems highly improbable. For in the space of possibility, for each way there is for the universe to obey the laws, there are infinite ways it might deviate from them. Quote: for each law-governed world, there are countless variants that would fail in different ways to be wholly law-governed. Derek Parfit in Why Anything? Why This? 2008. Why the laws hold is unknown to science. And yet, this feature of reality is the very basis that allows us to do science. A lawful universe is the basis of empiricism. It is why we can repeat experiments, and make predictions about the future based on past observations. But why does this work, and why should it work? Marshall explains the emergence of laws as a consequence of the computational reality. He says the laws are the consistent extensions of programs that produce the observer's mind state. Quote, "Arithmetic contains or executes all computations. Your first person is distributed on all computations going through your current first-person state. To make any prediction on the future of your possible inputs, you need to take all the computations into account, and the laws of physics is what is invariant in all consistent extensions." Bruno Marshall in Discussion List, 2019. Muller goes further, and gives a mathematical proof that shows why, given algorithmic information theory, observers will, with high probability, observe a persistence of regularities, i.e. laws. Quote, "That is, computable regularities that were holding in the past tend to persist in the future. Intuitively, highly compressible histories are those that contain regularities which can be used to generate shorter descriptions." Marcus Muller in Law Without Law, From Observer States to Physics via Algorithmic Information Theory, 2020. Because most programs are simple, and simple programs tend to keep doing what they have been doing, this gives the appearance of a fixed set of laws that holds into the future as the program unfolds. So in a sense, the laws of physics are the rules of the programs that instantiate us, as seen by those of us inside those programs. Why the laws are mathematical. It has long been recognized that mathematics is unreasonably effective in describing the physical laws. In 1623, Galileo wrote, "The universe is written in the language of mathematics." This connection between math and physics still puzzles scientists. Quote, "The miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift which we neither understand nor deserve. We should be grateful for it and hope that it will remain valid in future research and that it will extend, for better or for worse, to our pleasure. Even though perhaps also to our bafflement. To wide branches of learning." End quote. Eugene Wigner in The Unreasonable Effectiveness of Mathematics in the Natural Sciences, 1960. Mathematical patterns appear everywhere in nature. But why should physics be so mathematical? Tegmark offers a simple explanation: because physical theories result from our perceptions of what are ultimately mathematical structures. Quote, "The various approximations that constitute our current physics theories are successful because simple mathematical structures can provide good approximations of how a self-aware substructure will perceive more complex mathematical structures. In other words, our successful theories are not mathematics approximating physics, but mathematics approximating mathematics." End quote. Max Tegmark in Is the Theory of Everything Merely the Ultimate Ensemble Theory? 1998. Why the laws are simple. In the 2nd century, Ptolemy wrote, "We consider it a good principle to explain the phenomena by the simplest hypothesis possible." This rule of thumb is called the law of parsimony or Occam's razor. It is the idea that in science, the simplest answer that fits the facts is usually right. Occam's razor is no doubt a useful and effective rule, but until recently no one understood why it works. What is striking about the great questions of physics is their simplicity. Deep truths of nature can be expressed by short formulas, like F equals ma, and E equals mc squared. Physical equations rarely involve more than a few terms, rather than dozens or hundreds. Physicists are awestruck by this simplicity. Einstein remarked, "The eternal mystery of the world is its comprehensibility." Given there are far more ways for these formulas to be more complex, it's especially odd that they should be so simple. Quote, "Compared with simple laws, there is a far greater range of complicated laws. We would have some reason to believe that there are at least two partial selectors, being law-governed and having simple laws. Derek Parfit in Why Anything? Why This? 2008. Quote, "But the lesson is that, at present, the idea that the ultimate laws are as simple as possible is a hope, not something suggested by the evidence. Moreover, the prospect still faces the challenge of explanatory regression, as one would be left to explain why the underlying laws should be so simple." Sean Carroll in Why Is There Something, Rather Than Nothing? 2018. The mystery of simple comprehensible laws can now be answered. We have found a selector that preferentially selects universes with simple laws. Algorithmic information theory tells us that for each bit saved in a program's description, its occurrence is double. This adds up fast. A program that's 30 bits shorter, say 120 bits versus 150 bits, occurs 2 to the power of 30, or over 1 billion, times more often. Ray Solomonoff, the father of algorithmic information theory, was the first to draw a connection between AIT and Occam's razor. Quote, "On a direct intuitive level, the high a priori probability assigned to a sequence with a short description corresponds to one possible interpretation of Occam's razor." End quote. Ray Solomonoff in A Formal Theory of Inductive Inference, 1964. When Muller applied algorithmic information theory to observer states, he found that it led to the prediction of simple physical laws. Quote, "Observers will, with high probability, see an external world that is governed by simple, computable, probabilistic laws." End quote. Marcus Muller in Law Without Law, From Observer States to Physics via Algorithmic Information Theory, 2020. Why the laws are life-friendly. One of the most surprising discoveries in physics of the past 50 years was the discovery that the laws of physics and constants of nature appear specially selected to allow complexity and life to arise. Wheeler wrote, "A life-giving factor lies at the center of the whole machinery and design of the world. That the constants of nature, the strengths of the forces, the particle masses, etc., are just right to permit complex structures to arise is mysterious. Why are the laws this way? Why are they life-friendly?" Physicists ask, why does the universe appear fine-tuned? Quote, "As we look out into the universe and identify the many accidents of physics and astronomy that have worked together to our benefit, it almost seems as if the universe must in some sense have known we were coming." Freeman Dyson in Energy in the Universe, 1971. Quote, "The fine-tunings, how fine-tuned are they? Most of them are 1% sort of things. In other words, if things are 1% different, everything gets bad. And the physicist could say maybe those are just luck. On the other hand, this cosmological constant is tuned to 1 part in 10 to the power of 120, 120 decimal places. Nobody thinks that's accidental. That is not a reasonable idea, that something is tuned to 120 decimal places just by accident. That's the most extreme example of fine-tuning." End quote. Leonard Susskind in What We Still Don't Know, Are We Real? 2004. The first step in explaining fine-tuning is to recognize that for any universe to be perceived, requires that it be populated with conscious observers. This reasoning is known as the Anthropic Principle. The next step is to explain why any universe exists that supports conscious observers. Typical answers are that the universe was either designed or it is just one among a vast set of mostly dead universes. Quote, "We imagine our universe to be unique, but it is one of an immense number, perhaps an infinite number, of equally valid, equally independent, equally isolated universes. There will be life in some, and not in others. Carl Sagan in Pale Blue Dot, 1994. The existence of infinite computational histories guarantees that some will be of a type that can support life. Moreover, algorithmic information theory tells us the resulting physics should be maximally simple while respecting the constraint of being life-friendly. Quote: "In this paper I show why, in an ensemble theory of the universe, we should be inhabiting one of the elements of that ensemble with least information content, that satisfies the anthropic principle. This explains the effectiveness of aesthetic principles, such as Occam's razor in predicting usefulness of scientific theories." End quote. Russell Standish in Why Occam's Razor, 2004. And indeed, this is what we find when we examine our physics. Quote: "A very interesting question to me is the universe more complicated than it needs to be to have us here? In other words, is there anything in the universe which is just here to amuse physicists? It's happened again and again that there was something which seemed like it was just a frivolity like that, where later we've realized that in fact, no, if it weren't for that little thing we wouldn't be here. I'm not convinced actually that we have anything in this universe which is completely unnecessary to life." Max Tegmark in What We Still Don't Know, Why Are We Here, 2004. C. Is the universe fine-tuned? Why quantum mechanics? Quantum mechanics is a cornerstone theory of modern physics. It's among the most thoroughly tested of all theories in science, and it's given us the most accurate predictions in all of physics. But quantum mechanics is incredibly strange. It suggests the existence of many, infinite, histories, i.e. many worlds or many minds. Observation or measurement appears to cause the infinite set of possibilities to collapse to just one of the possibilities, and the selected result is absolutely unpredictable. According to quantum mechanics, no one can predict whether a photon will be reflected by or transmitted through a piece of glass, not even in principle. It's fundamentally random. Quantum mechanics includes apparent absurdities, like unobserved cats being simultaneously alive and dead, non-local faster-than-light influences, and unlimited computation underlying physical reality. Quote: "I have never been able to let go of questions like, how come existence? How come the quantum?" End quote. John Archibald Wheeler in Geons, Black Holes, and Quantum Foam, 1998. Of the mysteries in physics, how come the quantum ranks highly. Niels Bohr said, "Those who are not shocked when they first come across quantum theory cannot possibly have understood it." Werner Heisenberg admits, "I repeated to myself again and again the question, can nature possibly be so absurd as it seemed to us in these atomic experiments?" And Richard Feynman said, "I think I can safely say that nobody understands quantum mechanics." Wheeler thought if an ultimate theory could explain quantum mechanics, it would be a sure sign the theory was on the right track. Quote: "The most important test is whether it gives anything like quantum mechanics. If it does, we have a go-ahead sign; if not, we have to revise our thinking." End quote. John Archibald Wheeler quoted in Trespassing on Einstein's Lawn, 2014. Marshall's 1998 thesis, Computability, Physics, and Cognition, gave the first hints that features of quantum mechanics, such as indeterminism, the many parallel histories, the non-clonability of matter, and quantum logic, could be explained as a consequence of computationalism. Quote: "As in quantum mechanics, computationalism highlights a strong indeterminism, as well as a form of non-locality. Computationalism entails the existence of a phenomenology of many worlds or parallel states." End quote. Bruno Marshall translated from Computability, Physics and Cognition, 1998. Marshall writes, The quantum empirical clues happen to be serious hints that the physical emerges from an internally defined statistics on the numbers, dreams or computations, seen from inside. Standish went further. In a 2004 paper and in his 2006 book, he showed one could derive the basic rules, or postulates, of quantum mechanics, including the Schrödinger equation, purely from basic assumptions about observation within an infinite set of possibilities. Quote, "The explanation of quantum mechanics as describing the process of observation within a plenitude of possibilities is for me the pinnacle of achievement of the paradigm discussed in this book. I can now say that I understand quantum mechanics. So when I say I understand quantum mechanics, I mean that I know that the first three postulates are directly consequences of us being observers. Quantum mechanics is simply a theory of observation." End quote. Russell Standish in Theory of Nothing, 2006. Irreducible randomness. One of the strangest features of quantum mechanics is the presence of irreducible randomness that creates absolute unpredictability. Compounding this strangeness is the fact that the equations of quantum mechanics are entirely deterministic. And yet, when a measurement is made, it seems the universe momentarily stops following these equations to randomly select one possibility to make real, from among the many possibilities present in the equations. This was a pill too hard for Einstein to swallow. He declared, "God doesn't play dice with the world." And in the end he never accepted it. The single electron double slit experiment was voted the most beautiful experiment in physics. In this experiment, an electron is put into a superposition, where the electron exists in multiple locations at once. Then its location is measured. But when we measure the electron's location, it will appear in only one location, seemingly at random. Before measurement, it's impossible, even in theory, to predict where the electron will be. If we inhabit a computational reality, why do we see any randomness or unpredictability? Computations are perfectly predictable. Might this observation of randomness give us cause to doubt or rule out our being in a computational reality? The opposite is true. The existence of an infinite computational reality explains why we encounter absolute unpredictability. If only one computational history existed, observing randomness would be cause to dismiss the theory. But here there are infinite computational histories. Some of these histories will be similar to each other, some, so similar as to be almost indistinguishable. Since there are infinite computational histories, each observer's mind state can be found within infinite parallel computational histories. In a 1988 conference and in a 1991 paper, Mechanism and Personal Identity, Marshall explained how the appearance of randomness emerges from multiple instantiations of a single observer's mind. He calls the phenomenon first-person indeterminacy. Quote, "To predict the first-person observable outcome of any physical experiment, you have to assume that your current computational state will not be obtained in some other part of the universe, or the multiverse, with different output for your experience." Bruno Marshall in The Computationalist Reformulation of the Mind-Body Problem, 2013. In summary, no brain that belongs to multiple distinct universes, or computational histories, can ever be sure what it will see next. Multiple parallel histories contain identical instances of the same observer's mind state, or brain. A fundamental unpredictability and randomness will result from the observer's inability to determine which universe she's a part of, as she exists in all of them. Quote, "It is impossible for any observer to deduce with certainty on the basis of her observations and memory which world she is a part of. That is, there are always many different worlds for which being contained in them is compatible with everything she knows, but which imply different predictions for future observations." Marcus Muller in Could the Physical World Be Emergent Instead of Fundamental, and Why Should We Ask? 2017. So even in a fully deterministic reality, the existence of infinite histories makes the appearance of randomness inevitable. The physicist shining a photon at a piece of glass is in an infinity of histories where the photon will reflect, and is in an infinity of histories where the photon will pass through. The physicist can't tell which until after the experiment is performed and she learns the result. Ultimately, randomness stems from our inability to self-locate within the infinite sea of indistinguishable computational histories. Tegmark notes how randomness appears in deterministic processes. Quote, "It gradually hit me that this illusion of randomness business really wasn't specific to quantum mechanics at all. Suppose that some future technology allows you to be cloned while you're sleeping, and that your two copies are placed in rooms numbered 0 and 1. When they wake up, they'll both feel that the room number they read is completely unpredictable and random." End quote. Max Tegmark in Our Mathematical Universe, 2014. Einstein is vindicated. God doesn't play dice with the world. But perhaps, not even God can predict what universe you will find yourself in once you perform a measurement that splits yourself. See, does everything that can happen, actually happen? Infinite complexity. In 1948, Richard Feynman developed the path integral formulation, which provided a new way to understand quantum mechanics. Feynman showed that you get the same results quantum mechanics predicts by taking into account and adding up every one of the infinite combinations of possible particle paths and interactions. It was bizarre, but it worked. And this new formulation provided key insights that helped develop quantum electrodynamics, or QED. In 1965, Feynman, together with Shinichiro Tomonaga and Julian Schwinger, shared the 1965 Nobel Prize in Physics for developing QED. But why adding up all of these infinite possibilities gave the right answers presented a great puzzle, which bothered Feynman. Quote, "It always bothers me that, according to the laws as we understand them today, it takes a computing machine an infinite number of logical operations to figure out what goes on in no matter how tiny a region of space, and no matter how tiny a region of time. How can all that be going on in that tiny space? Why should it take an infinite amount of logic to figure out what one tiny piece of space/time is going to do?" Richard Feynman in The Character of Physical Law, 1965. Under quantum mechanics, an infinite number of things happen behind the scenes. The smaller the scales you look, the more seems to be happening, with no bottom in sight. The appearance of infinite happenings, infinite computations and infinite logical operations underlying physical reality is mysterious. Perhaps the simplest answer for why reality appears this way is, it appears this way because that is the way reality is. If infinite computational histories form the foundation of reality, then infinities in physics might just be a reflection of this reality. Quote, "In short, within each universe all observable quantities are discrete, but the multiverse as a whole is a continuum. When the equations of quantum theory describe a continuous but not directly observable transition between two values of a discrete quantity, what they are telling us is that the transition does not take place entirely within one universe. So perhaps the price of continuous motion is not an infinity of consecutive actions, but an infinity of concurrent actions taking place across the multiverse." End quote. David Deutsch in The Discrete and the Continuous, 2001. Quote, "Matter is only what seems to emerge at infinity from a first-person plural point of view, defined by sharing the computations which are infinitely multiplied in the universal dovetailer's work, when persons look at themselves and their environment below their substitution level. The non-cloning results from the fact that such a matter emerges only from an infinity of distinct computations." End quote. Bruno Marchal in The Computationalist Reformulation of the Mind-Body Problem, 2013. Quantum computers. Richard Feynman and David Deutsch are the two fathers of the quantum computer. Feynman proposed their possibility in 1982, and in 1985, Deutsch described how to build one. These computers exploit the unlimited complexity inherent in quantum mechanics to build computers of incredible power. How quantum computers do what they do is puzzling. Each qubit added to a quantum computer doubles its power. A quantum computer with 300 qubits can simultaneously process 2 to the power of 300 states. This number of states exceeds the 2 to the power of 265 atoms in the observable universe. How could a tabletop device process more states than there are atoms? How could it solve problems that no conventional computer could solve in the lifetime of the universe, even if all matter and energy in the observable universe were recruited for that purpose? Some found the abilities of these computers so incredible, they concluded quantum computers simply weren't possible. After all, where exactly would all that computation be occurring? Deutsch and Tegmark offer some answers. Quote, "Since the universe as we see it lacks the computational resources to do the calculations, where are they being done? It can only be in other universes. Quantum computers share information with huge numbers of versions of themselves throughout the multiverse." David Deutsch in Taming the Multiverse, 2001. Given engineering challenges, for decades quantum computers remained only theoretical. Today, quantum computers are a reality. In 2019, engineers at Google reported that their 53-qubit quantum computer solved in 200 seconds a problem that would take the world's most powerful supercomputer 10,000 years. Today, anyone can sign up for free to program and use IBM's quantum computers over the internet. What makes quantum computers difficult to build, is that to work, they must be completely isolated from the environment, such that they are not measured by anyone or anything until it finishes its work. By isolating the quantum computer from the environment, observers temporarily make their existence compatible with all the possible states the quantum computer might simultaneously be in. The parallel computations performed by quantum computers can then be explained by the work of parallel computational histories. Quote, "If current efforts to build quantum computers succeed, they will provide further evidence for the quantum multiverse, as they would, in essence, be exploiting the parallelism of the quantum multiverse for parallel computation." End quote. Max Tegmark in Parallel Universes, 2003. C. How do quantum computers work? Why time? The universe, our lives, and even our thoughts are inextricably linked with the march of time. Few things are as familiar to us as time, and yet time remains little understood. See, what is time? 2,500 years ago, Heraclitus recognized change to be the only constant in life, saying, "All entities move and nothing remains still." But it doesn't seem logically necessary for a universe to have time. Quote, "Mathematical structures are eternal and unchanging, they don't exist in space and time, rather, space and time exist in some of them. If cosmic history were a movie, then the mathematical structure would be the entire DVD." Max Tegmark in Our Mathematical Universe, 2014. Why should our universe have a property like time? All computers process information in an ordered sequence of steps. This ordering defines a notion of time that exists for any computation. Quote, "A Turing machine requires time to separate the sequence of states it occupies as it performs a computation." End quote. Russell Standish in Why Occam's Razor, 2004. Muller further showed that with algorithmic information theory, we can predict the appearance of a universe that evolves in time. Quote, "Our theory predicts that observers should indeed expect to see two facts which are features of our physics as we know it. First, the fact that the observer seems to be part of an external world that evolves in time, a universe. And second, that this external world seems to have had an absolute beginning in the past, the Big Bang. Marcus Muller in Could the Physical World Be Emergent Instead of Fundamental, and Why Should We Ask? 2017. Assuming we are part of an unfolding computation, then we should expect to find ourselves in a universe with time. A beginning in time? Current evidence suggests our universe has a beginning. But why should it? Until the middle of the 20th century, most scientists believed the universe was infinitely old, without a beginning. They considered theories of an abrupt creation event to be inelegant. Accordingly, scientists resisted the idea of a beginning until overwhelming evidence came out in its favor. It wasn't until we could actually see the afterglow of the Big Bang, in the form of microwaves, that scientists were convinced the universe began a finite time ago. We call this point the beginning because in tracing the history of the universe backwards, we hit a point where predicting earlier states breaks down and further backwards tracing becomes impossible. The physics either stops providing sensible answers, or we run into an explosion of possibilities and can't tell which of them is real. The theory of cosmic inflation gives an account of what caused the hot, dense, early phase of the universe. See, what caused the Big Bang. But inflation makes further backwards prediction, or retrodiction, impossible. It wipes its footprints with a set of infinite prehistories. Quote, since our own pocket universe would be equally likely to lie anywhere on the infinite tree of universes produced by eternal inflation, we would expect to find ourselves arbitrarily far from the beginning. The infinite inflating network would presumably approach some kind of a steady state, losing all memory of how it started. So the statistical predictions for our universe would be determined by the properties of this steady state configuration, independent of hypotheses about the ultimate beginning. End quote. Alan Guth in Eternal Inflation, Implications, 2013. Muller shows that algorithmic information theory predicts most observers will find themselves in a universe with simple initial conditions and an absolute beginning in time. He explains this reasoning for a hypothetical observer named Abby. Quote, if she continues computing backwards to retrodict earlier and earlier states of her universe, she will typically find simpler and more compact states, with measures of entropy or algorithmic complexity decreasing, simply because she is looking at earlier and earlier stages of an unfolding computation. At some point, Abby will necessarily arrive at the state that corresponds to the initial state of the graph machine's computation, where simplicity and compactness are maximal. At this point, two cases are possible: either Abby's method of computing backwards will cease to work, or Abby will retrodict a fictitious sequence of states before the initial state, typically with increasing complexity backwards in time. End quote. Marcus Muller in Law Without Law, From Observer States to Physics via Algorithmic Information Theory, 2018. This mirrors what cosmic inflation does for our universe. In an alternate history where humans developed algorithmic information theory before microwave telescopes, we might have predicted a beginning of the universe before telescopic evidence came in. Information as fundamental. Physicists are increasingly recognizing that information plays a fundamental role in physics. Scientists have long understood that matter and energy can be neither created nor destroyed. They are, in all interactions, conserved. But only recently have physicists realized the same is true for information. Physical information can neither be copied nor deleted. There is an equivalent law for the conservation of information. This discovery stemmed from the black hole information paradox. According to general relativity, dropping something into a black hole destroys its information, like an ultimate furnace. But according to quantum mechanics, information can't be destroyed. At best, a black hole can only rearrange information, like an ultimate shredder. In 1981, this paradox sparked the black hole war, waged by two camps of physicists. After decades of debate, the black hole war settled in favor of quantum mechanics. Information can't be destroyed, not even by a black hole. Physicists now understand a kind of mass-energy information equivalence. There is also an equivalence between entropy in thermodynamics and entropy in information theory. And constants of nature are closely linked to the ultimate physical limits of computational speed, efficiency and storage density. See, how good can technology get? Why is the link between physics and information so tight? Wheeler dedicated his life to the pursuit of fundamental questions. Ultimately, he reached the conclusion that everything is information. Quote, "It from bit symbolizes the idea that every item of the physical world has at bottom, a very deep bottom, in most instances, an immaterial source and explanation. That which we call reality arises in the last analysis from the posing of yes-no questions and the registering of equipment-evoked responses. In short, that all things physical are information theoretic in origin." John Archibald Wheeler in Information, Physics, Quantum, The Search for Links, 1989. Quote, "Now I am in the grip of a new vision, that everything is information. The more I have pondered the mystery of the quantum and our strange ability to comprehend this world in which we live, the more I see possible fundamental roles for logic and information as the bedrock of physical theory." John Archibald Wheeler in Geons, Black Holes, and Quantum Foam, 1998. Why is information fundamental? The answer is easy if reality is computational. Information lies at the heart of computation. In the end, all that computers do is process information. So to say, computation is the foundation of reality, is another way of saying, information processing is the foundation of reality. Quote, "The burgeoning field of computer science has shifted our view of the physical world from that of a collection of interacting material particles to one of a seething network of information." End quote. Paul Davies in the Flexi-Laws of Physics, 2007. Quote, "What we can learn from these reconstructions is that a few simple and intuitive constraints on encoding and processing of information will automatically lead to aspects of the Hilbert space formalism of quantum theory." End quote. Marcus Muller in Law Without Law, From Observer States to Physics via Algorithmic Information Theory, 2019. Observation as fundamental. Observation also appears to have a fundamental role in reality. Quote, "The universe and the observer exist as a pair. The moment you say that the universe exists without any observers, I cannot make any sense out of that. You need an observer who looks at the universe. In the absence of observers, our universe is dead." End quote. Andre Linde in Does the Universe Exist If We're Not Looking? 2002. Quantum mechanics revealed that observation somehow forces reality to choose from among many possibilities. More recently, physicists have speculated that the observer's power to force reality's hand applies not only to the here and now, but perhaps all the way back to the beginning of the universe. Quote, "We are participators in bringing into being not only the near and here but the far away and long ago. We are in this sense, participators in bringing about something of the universe in the distant past." End quote. John Archibald Wheeler in The Anthropic Universe, 2006. Quote, "The top-down approach we have described leads to a profoundly different view of cosmology, and the relation between cause and effect. Top-down cosmology is a framework in which one essentially traces the histories backwards, from a space-like surface at the present time. The no-boundary histories of the universe thus depend on what is being observed, contrary to the usual idea that the universe has a unique, observer-independent history. In some sense, no boundary initial conditions represent a sum over all possible initial states. End quote. Stephen Hawking and Thomas Hartog in Populating the Landscape, A Top-Down Approach, 2006. The observer might even, in some sense, choose the laws of physics. Quote, "It is an attempt to explain the Goldilocks factor by appealing to cosmic self-consistency. The bio-friendly universe explains life even as life explains the bio-friendly universe. Cosmic bio-friendliness is therefore the result of a sort of quantum post-selection effect extended to the very laws of physics themselves." End quote. Paul Davies in the Flexi-Laws of Physics, 2007. Can there be a universe if there is no one to call it home? Do observations themselves somehow define the histories and laws of the universes containing them? Observation and its relation to observed reality is an enigma. Wheeler believed the relation between them was our best clue to finding an answer to why there is something rather than nothing. Quote, "Omnibus ex nihil ducendis sufficit unum," Leibniz told us, "for producing everything out of nothing one principle is enough." Of all principles that might meet this requirement of Leibniz, nothing stands out more strikingly in this era of the quantum than the necessity to draw a line between the observer-participator and the system under view. The necessity for that line of separation is the most mysterious feature of the quantum. We take that demarcation as being, if not the central principle, the clue to the central principle in constructing out of nothing everything. John Archibald Wheeler in Quantum Theory and Measurement, 1983. In the view that all computational histories exist, observation does play a role in selecting both histories and physical laws. It is a tautology that observers only find themselves in computational histories capable of producing their observations. Since every imaginable program exists, implementing every imaginable set of laws, then in a very real sense, the observer does force reality to select both the laws and history they observe. Quote, "To derive the effective laws of physics, one needs to do statistics over the ensemble of identical observers. This involves performing summations over the multiverse, but these summations are with a constraint that says that some given observer is present." End quote. Saibal Mitra in Discussion List, 2018. It's curious that Buddhist thinkers reached similar conclusions about observers well ahead of modern physicists. Quote, "The Buddhist does not believe in an independent or separately existing external world, into whose dynamic forces he could insert himself. The external world and his inner world are for him only two sides of the same fabric, in which the threads of all forces and of all events, of all forms of consciousness and their objects are woven into an inseparable net of endless, mutually conditioned relations." End quote. Anagarika Govinda in Foundations of Tibetan Mysticism, 1969. Reviewing the evidence. We have found evidence in support of this theory. The existence of infinite computational histories predicts many features of reality. It predicts a universe of inviolable, but simple, mathematical, and life-friendly laws. It predicts a multiverse of parallel histories, infinite computational complexity, and a fundamental unpredictability, as we find in quantum mechanics. The theory predicts a universe that evolves in time, has simple initial conditions, and a point that we can't retrodict beyond, a beginning. Further, it predicts information and observation are fundamental. So far, all of these predictions are confirmed by current physical and cosmological observations. For the first time in history, humanity has an answer to why we exist that is backed by physical evidence.